Hello, I'm Carlos Rosso Suarez, and this is the CRS channel. I'm going to continue with physics problems in kinematics, and I'm going to try to finish problem 10. Okay, so let's pick up where we left in the previous video. We had obtained this expression for the position of the falling body, the free falling body, the falling body with air resistance. And we had this expression y minus y0 equals minus g over k times t minus 1 over k squared times g plus k v0 times e, or exponential of minus kt minus 1. So that means that y of t equals y0 minus g over k times t minus 1 over k squared times g plus kv0 times e, or exponential minus kt minus 1, which gives us y0 minus g over k times t plus 1 over k squared times g plus k v0 times 1 minus exponential of minus kt. Now, if v0 equals 0, that gives us y of t equals y0 minus g over k times t minus g over k squared times exponential minus kt minus 1, which is equal to y0 minus g over k times t plus g over k squared times 1 minus exponential of minus kt. This would be our final expression for the position in terms of time for the case which we have in which the body starts from rest. Okay, now one thing we must do is check out what happens, or what should happen, if k equals 0 for the expressions of both velocity and position. That is either this expression or this expression for velocity, depending on whether we want to make v0 equals 0 or not, or this expression, and either this expression or this expression for the position, depending on whether we want to make v0 equal to 0 or not. So we're going to use the following approximations. Here we have v of t equals minus g over k plus 1 over k times g plus kv0 times the exponential of minus kt, which is this formula here. So if you check out, we have then that this equals minus g over k times 1 minus e to the minus kt plus v0 e to the minus kt. So let's see, you can check up in the appendices of any physics textbook or a calculus textbook, and you can find the following series expansion for exponential of x. Exponential of x equals 1 plus x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed plus etc., 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 ellipsis. Now, if x is much smaller than 1, we can approximate our exponential of x to 1 plus x. Approximate exponential of x with 1 plus x. That means that one can approximate the exponential of minus kt with 1 minus kt. For k very much smaller than 1. That leaves us with v of t approximately equal to minus g over k times kt, is this, plus v0 times 1 minus kt. That would be placing this for this. And we're left with minus gt plus v0 times 1 minus kt for k much smaller than 1. If we make k equals 0, make k 0, then this term turns to v0, so we're left with v of t equals minus gt plus v0, which is the expression for the velocity for motion with constant acceleration, which corresponds to the free fall. Okay, now we will apply the same approximate, well, we're going to use this same series expansion to obtain another approximation for the exponential of x when x is much smaller than 1, which we will apply then for the position. So y of t equals y0 minus g over k times t plus 1 over k squared times g plus k v0 times 1 minus e, or exponential of minus kt. So here we take an extra term and we include this term here to the approximation. So we choose to approximate exponential of x to 1 plus x plus 1/2 of x squared. So we have y approximately equal to y0 minus g over kt, k, g minus g over k, that times t, plus 1 over k squared, that times g plus k v0, that times kt minus 1/2 of k squared t squared. So we have substituted 1 plus x plus 1/2 of x squared here, where x was replaced with minus kt, and we're left with this. So for k much less than 1, we have y of t approximately equal to y0 minus g over k, that times t, plus 1 over k squared, that times multiplying terms here. We have this expression here, and multiplying the 1 over k squared with each term within the parentheses, we get this expression here, and minus g over k times t cancels out with this gk over k squared times t. So simplifying here, we are left with y of t approximately equal to y0 minus 1/2 of gt squared plus v0t minus 1/2 of k v0t squared, for k much smaller than 1. So now if we make k 0, or we have k equals to 0, and this changes to y of t equals y0 plus vt, since this term disappears, minus 1/2 of gt squared. Okay, now after we have obtained these solutions and we have obtained the respective equations for v and y, and also replace the expression for v here and obtain the respective expression for the acceleration, we can try to create a table of values using different values for k, and obtain the different plots for the position, velocity, and acceleration, and check out what these curves would look like for different values of k. So we're gonna leave the discussion of the use of the spreadsheet for problem 10 for the next video.